Good afternoon, everyone. My name is Preetham. I am working in Trident Infosol as Sales Manager, South India. So today for the presentation and webinar, we will be focusing mainly on automotive model-based system engineering collaboration. So our main partner is Dassault Systems. To start with, we will give a small introduction about Trident. Yeah, Trident started our operations in the year 2000. Our main focus is product sales, design and manufacturing, and support activities. We have presence in Bangalore, New Delhi, Hyderabad, Mumbai, Chennai, Pune, and Ahmedabad. So as an organization, we are 200 plus people, and in the industry, we are known as a complete solution provider in software industry. So when we talk about software solutions, here I refer to the V cycle or the V cycle model development or software development. So we have products from Dassault Systems which cover in most of the stages of product development. So when you take any product, so it starts from requirement stage and ends in testing and integration stage. So if we refer to this model, we have at the initial stage of the requirements collection and management, we have Rectify, which is used for requirement management and traceability. Then we have a new product called ArgoSim, which is mainly for requirement validation. Then for system level architecture and specifications, we have CATIA Magic or No Magic, which is basically a SysML and UML model driven tool. Then for system design and development, we have Daimola, which is basically on Modelica language. Further going below on implementation as well as code generation, again we have CATIA Magic, which will generate a C code once you are done with architecture. We also have AutoSAR Builder, again, which is a simulation tool. Then on the right hand side, again at the testing stage, we have CATIA Magic, which can be used to validate your models. And as an integration of all these products, we have Innovia, or we also call it as 3D Experience Platform, which can be used in all these stages, and that will be very much useful for your overall product development and tracking. You can also follow Trident on LinkedIn as well as on YouTube. Just to give a small glimpse on today's speaker, we have Mr. Thorsten Gerke. He is a senior worldwide consultant on MBSE. He has total of 20 years of experience on model-based system engineering practice. He is currently working as a systems engineer solution consultant. Prior to joining Dassault, he had worked with Matchworks and Bosch. His education is MSc in Mechatronics and MBA in General Management. Thank you for your cooperation. Over to Mr. Thorsten. Thank you.
All right, so let me share my screen. Can you see my screen?
Yes, Thorsten, you're there.
Okay, very good. Yeah, also thank you for the quick introduction to Trident, and welcome everybody to this presentation. So as already said, my name is Thorsten Gerke and I'm working as industry process consultant for systems engineering at Dassault Systems. So purpose of my presentation today is to give you a first level overview about our model-based systems engineering solution here at Dassault. And there is primarily two things that I have prepared for this webinar today that I would like to discuss jointly with you. The first part of that presentation here will be a few slides that are going to portray our strategy for model-based systems engineering here at DS, which is based on what we are learning every day from our customers, based on the we do with our customers. And the second thing, and this is the major part of this session here today, will be a variety of different use cases and demonstrations that we are going to look at which will reflect different facets of model-based systems engineering, depending on the particular context of the project. So there's actually one term that will, let's say, primarily accompany us throughout the whole presentation today, and that is the term complexity. When we are sitting together with our customers and assess together with them their engineering processes to figure out what is the thing that can be done better, how can we improve the engineering processes at our customers, and how can we make things more efficient, there's one thing that always comes up that everybody's complaining about, and that is really the high level of complexity, especially in automotive. Complexity is something that is not restricted just to the automotive industry. Other industries are starting to face similar problems, but in automotive, it's something that is, I would say, quite extreme. I remember when I started more than 20 years back in the automotive industry at Bosch, things were already, I would say, quite complex. And we said at that point in time already, the industry needs to reduce that complexity because it's become really, really difficult to handle that. But what I have been observing over the last 2 decades, complexity has never been decreasing. It has been continuously increasing. And that's what everybody is really struggling with today. At that point in time, many years back, model-based development was making the claim to make a contribution to get a better grip on the overall complexity. And I would say model-based development as such is something that everybody is doing already in the automotive industry. I'm not really aware of any automotive company in the world that is not doing some form of model-based development. Some companies do it already very professional and very extensive. Others are starting or just in the middle. But I would say model-based development is something that is already well established in the auto industry. This is a topic as such that is nothing really new. However, one of the things that everybody is now working on and really trying to address is the next level of transformation. And that is to build really a continuity between all of these different modeling domains. Because in most of the cases, what we observe at all of our customers is they have a lot of models for different domains, but all of these different domains live in their own silos. So meaning these models are usually not really well connected to each other. And this is a significant contributor to the complexity that people are really struggling with. They've really lost control over how the different things are really belonging to each other. And that is what we are calling, what the industry is also stating, model-based systems engineering, making really a digital continuity between and throughout all of the different domains. That's the transformation that everybody is working on now in the auto industry. And that is also a key foundation for our strategy that is based on what we are learning every day at our customers. So on the one hand side, we are providing a solution to our customers that facilitates them to develop so-called cyber physical systems, which is nothing else than an evolution of what was called in the past mechatronics systems, so meaning systems that can be connected with other systems. So looking at, for instance, autonomous vehicles and the connection to the infrastructure, it's certainly a good example when you have an autonomous car that is getting connected and embedded into the parking system of a city infrastructure. That's certainly a good example for cyber physical system. Of course, when we look at automotive engineering processes and when we want to develop such experiences, there's usually many different stakeholders that are involved in such a process, many more than I can paint on a little PowerPoint slide here. I've just highlighted some of the typical roles that we see when we speak about model-based systems engineering. But there's usually many stakeholders involved coming from different domains. And one of the key assets that we from DS bring to the table as part of model-based systems engineering collaboration is a platform-based solution that uses a data model that facilitates a digital continuity between all of these different stakeholders and members as part of the engineering processes, with the overall goal to increase and improve the efficiency throughout the entire engineering processes and to fully digitize these processes. Of course, when we speak about automotive applications and automotive development, we all know testing is a very important thing, especially also when we talk about safety critical applications. And therefore, when we speak about model-based systems engineering, we talk about simulation as one of the key parts to test the system at all levels of the engineering process. And this is also a key part of the DS portfolio, providing simulation-based solutions at any layer and level of the engineering process. So it can either be, for instance, a complete mechatronic system simulation. However, we can also simulate things on a much more abstract level that you just simulate, for instance, an architecture, or we will see also later on in one of the demonstrations that we can also simulate textual requirements. Of course, one thing as part of an engineering process is to carry out the work to create engineering specifications, so really creating the actual engineering content that goes later on into an implementation. However, these things usually do not stand on its own. You always have some governance services and processes that are assembled around that. A good example for that is project management processes or change management processes that go along with these kind of activities here in the engineering execution. And a key part of our solution is that we build a continuity also from the engineering execution into governance services. And we will also see that today in one of the demonstrations. So when we speak about model-based systems engineering, this topic has a really federative mandate. So that means when you really want to bring together all of the different pieces and stakeholder to build a fully digitized process, you need to be very open. So that means you need to have really an openness that goes beyond the own platform solution. And it's something that we are doing really well, and we preferably do that based on open standards because we believe that our customers are really benefiting heavily from leveraging open standards instead of relying on proprietary solutions. And of course, in the auto industry, we have many standards. When we look at Modelica, for instance, for mechatronic system simulation, it's a very well-established thing. AutoSAR for building really software architectures for embedded software, or SysML that has really started to be a key part also in the automotive industry to develop the functional system architecture. So this is also the foundation for our overall product portfolio, which we refer as a model-based systems engineering solution from the S, which has two big pieces. On the one hand side, of course, we have the authoring solutions in terms of authoring apps where we create the actual engineering content. On the other hand, we also have the 3D experience platform that finally delivers the foundation and vehicle to build a continuity between all of these different authoring solutions, which can be authoring solutions directly in the platform or even special apps / standalone tools that have a continuity and connector into the 3D experience platform. That also brings to the table the governance services, including the data management itself, but also processes such as change management, issue management, project management, and so forth. When we look at the authoring part, it's primarily based on 4 different pillars. So on the very top, we have the area of system specification. When we look at this part here in particular, which refers to the design of the functional system architecture as part of the concept phase, which is done with our CATIA Magic solution and CATIA Magic Cyber Systems Engineer, primarily based on SysML, which we will see later on also in action, where we create the functional system specification and concept, which subsequently serves as an input to the detailed design of each of the different domains. So meaning once we have the functional specification in place, we need to open our mind and decide what are the pieces that go later on into hardware and what are the pieces that go later on into a software implementation, and how do we design also, for instance, the physical plant. And all of this authoring content that we create here can also subsequently used for testing purposes in our simulation solutions. And we will see also demonstrations for that later on. Of course, requirements always play a very crucial role, and this plays also a very crucial role in our solution, because at the end of the day, requirements are the things that we want to finally satisfy. They often come from our customer, and we want to make our customer happy. So we have to, at the end of the day, satisfy all of the requirements. And we make requirements also fully traceable using the solutions in the 3D experience platform. And traceability is not just traceability among requirements. We do it fully end-to-end, so we can trace from requirements over the architecture into the detailed implementation, and the implementation can be either a piece of software or it can be, for instance, even a 3D CAD. And we will see also demonstrations for that later on. Okay, so let's come to a very first example to see what we mean by digital continuity and how we can do that using the 3D experience solution and platform to finally establish a model-based systems engineering collaboration between different stakeholders of a development process. So what we are wanting to take a look at is that we are going to develop here a little electric vehicle system, and there's primarily 4 different steps that we want to go through. So first of all, we have a team that is sitting together in that process and starts on a very high level to do some collaborative ideation. So we are brainstorming what are the things that should go later on into the overall experience for the customer, into the car, and then we start to formalize and turn that into structured and formalized requirements. From that, we finally derive a system architecture and do an implementation of that vehicle. And in order to assess the performance, we run a simulation to assess really if the performance meets the requirements that we have sketched out here initially. And then we are also going to see that we are going to detect a problem with our current implementation. And that problem is being picked up and escalated, and we start to turn that into an issue, and we're going to manage that issue. So that's an example that shows very nicely how we connect the different steps as part of a process to bring together all of the stakeholders in a fully digitized process. All right, so let's take a look at this little example. So what we are seeing here is the graphical user interface of the 3D experience platform, where we have the different roles, and each of the roles has so-called apps to do the job. And we are starting in Swim. This is a collaborative team environment. It's like a community system where people can make posts in this community. Others can finally like it, make comments to it. So it's about starting the ideation process on a relatively high and abstract level to gain insights, collect ideas, opinion for things that should later be turned into formalized requirements. So these are the people that are finally working on the project. You see people from different domains, each has a particular role in that project. So we have picked some of the ideas and started to turn it into really formalized requirements. This is our requirements management solution. You see on the left the requirements objects. On the right, you see the detailed description for each of the requirements. So we are now going to set up a meeting with our team in the 3D experience platform because we want to review the status of our vehicle project, because there's primarily 2 things where we have some problems that we need to really investigate a bit more in detail. So there's primarily 2 things. One is relating to the battery and the other one is relating to the powertrain part. We are currently exceeding the budget that we have been targeting, relating to the battery and the powertrain part. And for the powertrain, we are investigating a new solution from another supplier, and we want to embed a new motor. But we have to test if the performance of that new motor is really meeting the performance needs of our car. So we go back to our requirements solution that we have seen already previously, and we have one requirement in our requirements solution defined, which is a quantified requirement in terms of the acceleration of the car, so part of the overall user experience that we want to provide to the customers buying the vehicle. And that acceleration from 0 to 100 should occur within a certain amount of time, and that is certainly a key performance factor that we want to now verify. Yeah, so we change that, it should be 3.1 seconds. And we have derived from our requirements a functional system architecture for the powertrain part that was created in CATIA Magic in SysML, and I then imported it into the 3D experience platform. And this one is going to be equipped also with a simulation model underneath to finally evaluate really the performance of our vehicle. So you see the same architecture here, and that is equipped with a simulation model underneath. So we see, for instance, here an evaluation of the performance. At the moment, we see the acceleration. It's not addressed yet. So we have to run a new test with the new system. And the test is being done based on the Modelica model that we simulate with Daimler in the 3D experience platform. So this is at the end of the day nothing else than an executable digital twin that we can put on the virtual test track to assess the performance of our system. We see from 0 to 100 we are at 2.9 seconds. That's good, so we have met that requirement. Okay, but we also have another experience in our car, and we have some level of autonomy in form of an autonomous emergency braking system. Yeah, and from the test it occurred, we seem to be having a little problem with this one. So this here is another facet and view of our requirements management solution compared to the one that we saw previously, where we have some sort of word-like experience. We have here a management cockpit where you have more an Excel-like experience, depending on which view you prefer. And we see our requirements criterion for the advanced emergency braking system. And there's a test case that has been defined for this one. And the test was actually executed, and we see here it has been flagged in red because the test revealed that the performance need has not been met because the obstacles in front of the car have not been properly detected. So that means we have a technical issue here because the requirement has not been satisfied. So if we have a technical problem, that means we have an issue here. So that means we need to file an issue against that because we want to resolve that. So that's another continuity. We can directly go from our requirement solution into an issue mode. So that means we can start to create an issue directly from the requirements, give it a description to say, okay, the obstacles are not properly detected. And then we want to also escalate it because we are really getting to our deadline. And it's actually a high priority, of course, and it's a defect that we have encountered here. So we give also a hint for the resolution because we have recently made a software upgrade, and we believe the problem is most likely relating to that. But at the end of the day, it's up to the guy that finally has to investigate the implementation, or is in charge of the implementation. So the test procedure is actually specified also in the test specification, a different document here in the platform. And we now give also the issue a title. This is a title that will pop up later on in the issue list of the app, where I can see all the issues that I'm involved in. So when we press OK, this issue is being produced. We get a confirmation the object has been created. So now we go into our issue management list from here. So we switch the view. We go back into another tab of our dashboard solution. And we see here, there's a new issue that has been created. And you see the list of issues where I am actually involved in. And it's the new one that I just created. And you see the test case is automatically associated to it because I've right away created it from the requirements app. Now I can add also additional information. I add also the artifact of the software to the test case itself. I don't have to, but the more precise I am, the better it is to understand the issue and to deliver all the attachments to it. And now I have to assign also a person to that. In this case, it's Romain, our software engineer, who is going to follow up and is now in charge of pursuing and fixing that issue. I think this example here gives you a very first idea of what we mean when we speak about a digital continuity as part of a model-based systems engineering collaboration using the 3D experience platform to fully digitize an engineering process. Of course, there would be other pieces following after the issue creation, but for a first part, this is already a well-digitized process. Pavan, are you going to start the polling question section 1?
Yes. There you go. There's the first polling question. The audience, please feel free to answer them. There we go. There is a second polling question for you. Thank you so much for participating in the poll. The presentation continues. Torsten, you can please go ahead and start.
All right, thanks. Okay, let's continue our journey. And we also make the continuity now with that what we have seen in the first demonstration for this electric vehicle. There was at the end this AEBS functionality that we were looking at and where we filed an issue because we identified a problem with that. What we are wanting to do now is that we are wanting to look at a possible exemplary process, how we can develop such an AEBS function that should later go also into a software implementation. And we primarily want to look at the process, how we can use a systems engineering approach in a fully continuous and connected manner, where we get from the requirements later on step by step into an implementation. So I have created and sketched out the macroscopic process that we are going to follow also in our demonstration in a few minutes, where we are going to start at the very top with a bunch of stakeholder needs and requirements, as we've seen previously in our requirements management solution. And then we take those requirements for AEBS system and start to analyze and refine and decompose that into a functional system architecture proposal in CATIA Magic using SysML. Then we have this functional specification, and we are going to start more to go into the domain specific part. So meaning we are taking those functions and start to allocate them on an EE hardware topology to say where will each of these functions later go in the hardware topology of our EE architecture. Of course, at the end of the day, we do not stick with functions because we have to produce software that should later on be deployed and flashed onto each of the ECUs. And we have capabilities, this is also part of our continuity, to synthesize from a functional architecture directly a software architecture. So we have a full continuity here also in the 3D experience platform. So that means we end up then with a software architecture. And what we are wanting to do is, given that we are now speaking here about automotive applications, very often software architectures and implementation in automotive are AUTOSAR based. So what we are wanting to do then is also to make it AUTOSAR compliant implementation. And part of the whole story is then that some of the software pieces, aside from the architecture, might have been also created in other tools. For instance, you might be using Simulink to produce some of the, or to create some of the algorithm for a controller, for instance, use code generation with embedded coder to produce the application layer code, and marry that also with the AUTOSAR-based software architecture. Usually, very often, the software content are then managed in software configuration systems, such as Git, for instance, where you manage, for instance, the detailed code that you have produced, the C code or C++ code, depending on what you prefer to use for your application. And we will see also in another demonstration following the next one, how we can then also keep up the continuity between all of these different assets and content by building up a full end-to-end traceability from the initial requirements over the architecture down to the EE architecture, into the software architecture, and even into the software code that is being hosted outside of 3D experience in an external Git repository. And we can even go so far that we build a hybrid BOM in terms of a mechatronics BOM, where we combine, for instance, hardware elements and software elements. Yeah. So before we go into the demonstration, one of the things that we have seen initially is also, aside from the actual creation of engineering content, we also have the capabilities that you can build a continuity between the actual project management and the engineering execution. So we see very often at customers of ours that people are using for the project management part of their complex projects, they use a software where they sketch out and build the complete project plan, including the schedule, the tasks, and finally the resource planning to make sure everything is stuffed and on schedule. They use a software for that does the project planning quite well, but usually it doesn't have any continuity into the actual engineering execution, and in particular into the tools that are used by the different engineering teams. This is very much different with our platform-based solution. So that means when you use, for instance, our project management solution, you also the project plan, you sketch out the different tasks, And all of these tasks have a direct continuity into the actual engineering execution. So that means when you define a task here, this task is going to show up in the collaborative task management dashboard of the engineer that later on has to work on that particular task. And you can assign inputs to that or attach inputs to that. Could be a specification that helps him to do the next level in the downstream engineering work. And he can also return the artifacts that he has created. The benefit of that strong continuity of project management into engineering execution allows you to keep full track of where you are with your project. So what are the things that have we done already well, but more important, what are the things where we have still some open issues to resolve, and where do we have potential things where we even need to start to escalate that? So meaning when we then speak about a traceability, this traceability is not just limited to the engineering content, we can do it throughout the whole project, and it makes it very easy when you need to go into assessment and reviews by external audits, for instance, that you have a full traceability throughout the entire project. Okay, so let's take a look at another demonstration that shows how we bring all of these things together, in particular for the AEBS system, and now just not only the engineering execution that we've seen in the V diagram, but also combining that with project management. So what we are seeing here is when we start this demo is actually our project management app in the 3D experience platform, where you see, for instance, the schedule of our project. We have a project space here, and where we have different phases of the project with some individual tasks and people that are assigned to that. You can also display that as a Gantt chart. We will see that later on in the demonstration. So there's a couple of things that we have to work on. And one task is, for instance, also define the vehicle functional system architecture. That will be a primary task now in the beginning. So we also have a KPI view for the projects, where you see really at a glance, where am I right now with my project, and where do we have some problems that we finally need to follow up on. All right, so let's start now with the actual engineering execution work. And this means we have to do some work here. We have queried out also some requirements for our autonomous experience. So there's, aside from the AEBS, also a couple of other ADAS features that we have sketched out as requirements that should go later on into the car. And some of these requirements relate directly to the AEBS system. So these requirements that we've authored in the 3D experience platform can be directly synced with CATIA Magic through Data Hub, which is a solution to bring the requirements directly into CATIA Magic. Yeah, so that can happen fully automatically. You don't need to move around any files or something like that. So now we have these requirements in CATIA Magic, when we are using now SysML to do an analysis of those requirements and to sketch out later on a structure of our system that should then later on be implemented. So that means we take these requirements, start to build use cases fully compliant with SysML, and investigate what are the functions and services using activity diagrams that will be needed to materialize the requirements. And then we end up with a first level structure for our system. And of course, in order to describe the behavior, we have created a first algorithm in form of state machine that reflects and mimics the behavior that we expect from the AEBS system. The really powerful thing in CATIA Magic is we can simulate all of that stuff. We do not need to produce code for that. We can do that right away in the model and run a simulation of the functionality to assess if the behavior of the algorithm is properly materialized. So we are playing around, for instance, with the time to collision here, but also look at different conditions. What is if we turn on and turn off the system, or if there's a defect? We see the algorithm moves into the proper mode. And then we decrease, for instance, the time to collision. So meaning the car in front of us is getting very close to us, and it's getting super close. And now it means we have to deploy a full brake, and we see, okay, the algorithm is doing the right thing. So meaning we have first tested our system and we see it's properly functioning. So that means the next step in our project, and you see again our project management app here, is to allocate the new function on an EE architecture. And you will see the task that we have here will pop up in the collaborative task dashboard of the engineer that is going to run the next step for the allocation on the EE architecture. So this is the EE hardware topology that we are going to use, on which we want to deploy that function. You see a bunch of ECUs, a bunch of high-speed CAN buses. That was on the top, a central gateway. And you see this collaborative task dashboard here, where we have this task popping up in the dashboard of the engineers now working on this task, which was previously defined in our project management app. And this is the nice continuity that we have in the 3D experience platform, that you now have the continuity also into the engineering execution. And we have directly attached also from the upstream part all the specifications that were created upstream, so that we have a continuous starting point for the guy that is now in charge of the allocation for the EE architecture. You see on the one hand side the textual requirement specification, and we see now the functional interaction chain that was previously sketched out in CATIA Magic. So this one has now been allocated onto the EE hardware topology. So I've done that already up front. And we see when we select this function here, we see on which ECU this is going to be hosted. Or if we do it the other way around, if we select one of the ECUs, we see which functions it is hosting. So very nice traceability of the allocation. So this stuff is also fully integrated into our variant and configuration management, which is an important part for automotive applications. So I have a bunch of configurations, vehicle configurations here defined. When I apply them to my system specification, I see that some components are grayed out. These ones are not belonging to these configurations. So you can very easily do variant configuration management based on the 3D experience platform. So we can also do some first computation and estimation, for instance, of the bus load of the system. So in the next step, we need to get now from a functional architecture to a software architecture. And as previously said, we have a continuity in the platform where you can synthesize that automatically. You also can do that manually if you prefer. We provide both ways to do it. But this is part of our digital continuity in the platform. So that will be the software architecture with the different ports and interfaces. So as I said previously, at the end of the day, we want to get down to an AUTOSAR compliant software implementation. So what I've done now based on the software architecture that I previously synthesized, I've taken a small part of that and exported that as an AUTOSAR XML file and brought that into our DS AUTOSAR authoring solution, which is called AUTOSAR Builder. So this is a Dassault tool where you can do the authoring for the AUTOSAR application layer software. So we see a software composition here, including two atomistic software components, which has been authored in a fully AUTOSAR compliant fashion, where you have the different port, for instance, for the atomistic software components. So when we go onto one of the atomistic software components and we go into the details of it, we will see the different port definitions, and we will also see that this atomistic software component also has an internal behavior. So this is part of the more detailed refinement now to do really the detailed AUTOSAR-based authoring. We see, for instance, 3 different runnables, and each of these runnables is becoming exactly one C function later on. So fully compliant with AUTOSAR, where we also have the RTE access points and APIs that let these functions talk to other functions in the car. It's a very important thing and part of the AUTOSAR standard, because it makes it very easy later on for the application software developer to connect this application code to other software components. So one thing that we can do now is the so-called Rte Contract Phase. So it means that we are producing all of the header files that include the RTE API descriptions, because this is part of a contract, for instance, between OEM and supplier, where the OEM may deliver, for instance, the header files to the supplier to specify the interfaces, the inputs and outputs. So we see the different RTE API functionalities, and these are the functions that later on the software developer would use to connect his software function to the inputs and outputs and have it communicating with the rest and other software functions. We can also produce for the different runnables templates, so which are then primarily the bodies of the C functions that would later be deployed on an ECU, so turned into a binary and flashed onto the ECU. So we have a couple of templates that are predefined. So when we go to runnables generator, we can use one of the default templates. You can also create your own template, and then we can produce from that description here some predefined bodies for the different C functions. So we just select the place where we want to store that material, click on OK, and then we produce the code or the body for the different C code functions. So when we open one of the source code files, we see, for instance, here on the one hand side, the header file that was previously created in the Rte Contract Phase. And further down, we see then a definition of the runnable, where we see the body of that function predefined. And we have here the inputs, the outputs that were part of the Rte Contract Phase definition. And the application developer can then place his code here and connect that to the inputs and outputs. So very easily. All right, I think that's also a very interesting example that shows another facet of a continuous approach in a model-based systems engineering fashion, how you can develop a software-based function, really starting from the initial requirements over to the design of a functional system architecture using CATIA Magic and SysML, and then go into the detailed domain design of an EE architecture and further down to the software implementation. So this was, let's say, continuity on the design side, on the left side of the V. But what I've said previously is also that we can do also an end-to-end traceability. So what do we really mean with end-to-end traceability, and what's the value of using a traceability at all? People like you that are working every day on these kind of applications, I'm pretty sure many of you are also dealing with standards such as ISO 26262 or Automotive SPICE. And these standards, for instance, explicitly demand to have also a traceability in the entire process. And there's a good reason why that is the case. So let's take a look at this particular use case here. Let's assume we are in the middle of our development process. So we have already sketched out a whole bunch of requirements and used them to come up with a functional system architecture specification, and even went a bit further and already sketched out specifications and content for the detailed domains for hardware and software. But now let's assume our customer is coming to us and says, okay, we have decided that we want to change a requirement because we feel what we have sketched out initially was good, but there's one thing that we need to change because we want to improve further the overall user and customer experience. So if we get such a request from our customer, the first thing that we are doing is we will sit down and ask ourselves, okay, if that requirement here is going to change as a request of the customer, what does that really mean for us in engineering? What are the things that would be impacted because they would need to be changed based on the change of this requirement? There might be many things that might be impacted. It can be even go up that we need to make architectural changes because that requirement is now supposed to be changed. Why do we want to know that? Very simple. We have to assess, do we have at the moment really the resources to do the change? Because we may have a deadline that is coming up where we need to have the people in place to do that change. We want to figure out what is the cost relating to the change because we want the customer to pay for it. And we need to assess really the overall risk. Can we do it or can't we do it? And if we can't do it, then we possibly want to convince the customer to not do the change because we feel the risk of that change is simply too high. So based on that, we make a decision, a go or a no-go, if we do it or not. If we decide to go for it, then we have to introduce the change planning, implement the change, and then we are back on track. So not looking now at the entire change management process here, that would be a bit too complex for the session for today, but looking more at the systems engineering part and what role can it play here as part of the whole process. Well, when we look at this thing here, one of the key elements that we need is an impact analysis to figure out the paths and elements that would be impacted if we get such a change management request. And systems engineering, in form of a model-based systems engineering approach that includes an end-to-end traceability, can exactly address that task. So meaning you can quickly figure out with an impact analysis, if you have a full traceability, what are the things that are going to be impacted if we were changing that requirement. So how can we do that? Let's take a look at a typical example of our customers in the auto industry for an end-to-end traceability. So this example here is, aside from showing the end-to-end traceability, also aims to show the openness of the platform, because we are bringing here content together from various external resources, repositories, and databases. So we see here, for instance, on the left, so overall is again our AEBS system that we have seen previously, but now in a traceability view. We have here on the left a whole bunch of requirements. We have, for instance, some requirements that were created indoors. And these requirements are also managed indoors, and we just look into the doors database and make that part of the traceability. We have some requirements also sketched out in PDF, at work, at Word, and we can build that also into a traceability. And then we have our functional system architecture that was carried out in CATIA Magic, and the data is stored in Teamwork Cloud, so also managed externally. And then we have done the partitioning, which pieces go into hardware, which pieces go into software. And the software elements, one is, for instance, a model in Simulink for the controller, as well as the source code implementation are both also managed externally in Git repositories. And then we have also a hardware part that relates finally to the ECU, and that's managed directly in 3D Experience. So let's take a look at how we can do a traceability on all of that stuff. So the first thing that we are wanting to look at is, you see here in the tree all the requirements that are available in DOORS. So this is the DOORS client here. I've created some requirements, some functional requirements in DOORS and stored it in the DOORS database. And we just link into the DOORS database, so we don't duplicate any information. So let's go into the traceability graph. We see here the traceability graph, and we see these lines here. These are the traceability relationships and links between the different artifacts on the different layers. And when we select the requirement in DOORS, we see in impact mode right away which would be the elements in the downstream path that would be impacted if we were changing that requirement. And this goes even down to the software, which is stored in an external Git repository. Now you see the impact analysis right away points us to the function in the code. So we do not need to look for or search for it. The impact analysis does the job for us. From this engineering bomb here, we see that element was also affected. This is at the end of the day the ECU, the 3D CAD for the ECU that would be actually finally impacted. And we can down to any level of the traceability. You always need to make a trade-off. How far do you want to go with the traceability? Because it's something that also needs to be maintained over time. So let's go a little bit back to the requirements that we had created in DOORS and select the requirement again. We see in the downstream path, we also have a Simulink model, and that's an interesting aspect of our solution. We can also view the content of the models and the diagrams without having the tool on the machine. I don't have Simulink here on my computer, but I can still view the Simulink model. This is very, very useful when you want to review content with other people. So we can do the same also for PDF documents. I have labeled a bunch of requirements here in the PDF document and can do the same impact analysis with a PDF document. And we can also do it bottom up, not just top down, to see if I change something downstream, to which requirements do I have to still comply. So this is one very short, let's say, example and snapshot of what you can do with an end-to-end traceability. All right, so Pravin is now going to launch the second section for the polling part.
Thank you so much, Thorsten. There you go. There's a polling question for you. Audience, please have your poll. There's another polling question. Okay, thank you so much for answering the poll. I would like to inform the audience out there to ask you a question in the chat box, in the chat window. So at the end of the webinar, we have a Q&A session where Thorsten is going to answer all of your questions. Thank you. Thorsten, there you go.
Okay, let's make the continuity again with what we have previously said. So another important part of the development in automotive is, of course, let's say, safety engineering. We often have to deal with safety relevant applications, and I think the auto industry has always been doing a very good job when it comes to addressing the safety needs to make the mobility experience safe. When we look at new trends in the auto industry, such as autonomous driving, vehicle electrification, of course, there's new topics from a safety point of view coming up that have to be addressed. And as always, safety must be part from the initial design phase on already when we sit together, sketch out requirements. Safety must be part of that and not just something that is being put on top at the end. So that means it requires also that we have many different stakeholders, again, working with each other. When we look at typical suspects, such as a safety expert that is owning the safety process as such, who is going to work with other people, reviewing content, for instance, figure out, are we doing the right things or do we need to add additional safety measures? But this guy at the end of the day also needs content from other people. Good example is, for instance, the collaboration with a system architect that is in charge of sketching out the functional system architecture that should be reviewed together with the safety expert, but plus maybe also other people. I still see today, when we look at the processes of our customer, there is people that still use PowerPoint or Excel spreadsheets to do these kind of things. You know, there's Fmea analysis carried out and stored in Excel spreadsheets. There's architectures that are painted on a PowerPoint slide. That is certainly not a professional way of working because there is no connection between these elements. You don't have any traceability between these elements. And if you don't have a traceability, how do you want to do a good change management? Yeah? It's much better to use a model-based systems engineering approach where all of this data is linked with each other. Of course, when you speak about safety engineering for systems, a key part of that is to develop a functional and technical safety concept that we want to end up with. And when we look at the new vehicle project, one of the initial things that we do in order to get there is to carry out hazard and risk analysis. So where we identify what are the top level vehicle functions that will go into the overall experience and look at what is the hazardous potential that arise from them if there is a malfunction behavior out there. So we don't need a detailed architecture for that because we are really just at the top level behavior of the vehicle, a top level experience. From that, we derive, for instance, the ASIL level, but also the top level safety goals that we want to finally make sure that they are never going to be violated. But then, of course, we need to start detailing out the system architecture, but concurrently to that, we also have to make sure that our safety concept is being evolved and implemented and becomes part of that overall architecture. There's, of course, analysis such as fault tree analysis, failure mode analysis that can be applied on different levels of the architecture to help us deriving new requirements from that. So the overall intent of these types of analysis is always to create new requirements to finally go into the specification and implementation of the system. Of course, this is not a one-time process. This is a highly iterative process where the different groups need to concurrently work on the overall solution. In order to support that process really well, the system architecture is, of course, let's say, in the center of all of these activities. And our system architecture design tool is CATIA Magic Cyber Systems Engineer based on SysML, where you create the functional system architecture. And we have a couple of solutions to support the safety engineering process extremely well. One of them is, for instance, the ISO 26262 functional safety plugin, which is based on the new OMG RAML standard that allows you to carry out the complete hazard and risk analysis. This is a multi-step process, which is then the starting point to derive from that a functional safety concept. And we're going to see that later on in the demo, how that works. The other thing that we have in our solution is the Safety and Reliability Analyzer plugin that allows you, for instance, to carry out an Fmea analysis. So you see the Fmea table here. The table, of course, is just, let's say, the aggregation of the results of your analysis. It's not the analysis itself. The analysis is something that you carry out on the system architecture model directly in CATIA Magic, where you go through the architecture together with other reviewers to figure out what are the things that could go wrong in that architecture, what are the malfunctioning things, and how could that propagate throughout the system? What are the things that we need to insert into this architecture to ensure that this is not really starting to become a big hazardous problem? And that information and introspection goes then later on into your Fmea table. So let's take a look at a quick demo in CATIA Magic, how we can use these solutions in order to do safety engineering for systems. So we are going to start in the first step to look at the ISO 26262 plugin, how we carry out a hazard and risk analysis, use that to derive from that a functional safety concept. And in the second step, we also look at how we can use the reliability plugin to do, for instance, Fmea analysis. So these are different steps to carry out a hazard and risk analysis. And this here is a HERA table where we have one of the hazardous events. We see which function is finally relating to that, which ASIL has been derived from it, and what safety goal have we defined for it. And all of these are elements of the model that have been previously identified and created. And we do here the aggregation of all of that. So if we start at the very first, we identify first what are the top level functions that could fail and what is their potential technical problem. Without specifying any hazard here, it's just about looking what could go wrong from a technical standpoint of view. So in the second step, we look at possible driving scenarios, really just the driving situation that could occur. And we also say, okay, what's the level of exposure? So how frequently can that finally happen? And then we bring these two things together and look at the possible accident scenario. So we have this malfunction in behavior and what accident scenario could occur and how controllable is this by the driver. And then we end up with identifying what would be the overall effect of that. So we identify the severity because this is important. Then we have the three factors in place from which we can derive the ASIL. So this is being automatically determined. It is defined in the ISO standard, how it comes together based on these three factors. And the really important thing is all of this data is linked with each other. So if we change, for instance, in the driving scenario, the level of exposure, you see in the HERA that it automatically changes this here, and it automatically also changes the ASIL because the data is linked with each other, and the ASIL is a function of these three factors. So if we go back and change that value for the exposure back again to what it was previously, then we will get to that what we initially had also in this HERA table. So if you change it again back to exposure level 4, we see, okay, we are now at the point where we have been already previously. Yeah. And we aggregate, for instance, also automatically all of the safety goals. In this one, I've just defined one. Usually have a very exhaustive list when you work on a bigger system. And that is the starting point to create also, start to sketching out the requirements as part of our functional safety concept, where we have the top level requirement at the safety goal. And then we start to derive and do a decomposition of the different requirements that we need to embed to make our system safe. And if you want to do an ASIL decomposition, we have also special stereotypes for the relationships. So if you want to further decrease the ASIL because you have ASIL D here and you say, okay, I want to decompose it into two components to decrease the ASIL level, we have specific stereotypes to label that. And then you can further drill that down into the different requirements for the different technical domains. Of course, when we talk about safety critical applications, you always want to make sure we also have a safe state. So for a steering assist system, in the absolute worst case, you could say, okay, we turn that functionality off. That might be a possible safe state. So how can we use now the reliability plugin to carry out an Fmea analysis? This is a different system here, where we're going to do an Fmea analysis, for instance, for the lighting part of this vehicle system. Creating an Fmea is very easy. So we go to the Fmea table, we create a new Fmea item. We select to which domain does it relate, and this one, the electrical. And the system under consideration is actually this one here. So we have actually later on this light instance is actually instantiated in that system here. So we pull that now directly from the architecture. And that's the continuity as part of a model-based systems engineering approach. You take the part property from the system architecture definition and actually embed it into your Fmea analysis. Yeah, so that's the part property that has been instantiated here. And that is actually the instantiation of that subsystem as part of the overall vehicle system. So full continuity between system architecture and the Fmea table. So now we need to define also failure mode. I've done that already up front. We have specific stereotypes for that. I say, okay, the light does not turn on. That is the failure mode of that system or that component. And then we also need to say, okay, what's the local effect of that failure? Of course, if the light doesn't turn on during the night, we lose the illumination in front of the car. Makes it hard to detect, for instance, other obstacles. Okay, now I can make the bridge also to what I can define for the upfront. If I've carried out a hazard and risk analysis, for instance, I can make really the link back to this one here. So you see I've carried also a hazard and risk analysis, and I can reuse that information now also in my Fmea table if I want to make the bridge to the hazard and risk analysis to say what is finally the overall vehicle level effect. So I say, okay, I lose the ability to recognize traffic objects because the illumination in front of the car is not available. So then, of course, when we do an introspection of our system architecture, we also understand much better what's the cause of the failure. So in this case, I say, okay, the sensor that's finally in charge of detecting the illumination is not properly working. And last but not least, we said we also want to use this analysis to create new requirements. In this case, I say, okay, if that functionality is not working, I want to inform the driver about the malfunctioning of the lighting system. So I've created a new requirement object here and add this to my Fmea table. So full continuity also between system architecture, requirements creation, and the actual Fmea table. Yeah, I think it's a very nice example that shows how you can use a model-based systems engineering approach to ensure continuity between design and analysis. All right, before we move on to the last example, Raven also has another set of polling questions for you.
Yes. So there you go, audience. We have the next poll for you. All right, we go for the next poll. Thank you so much for answering the poll. We'll continue the presentation.
All right, thanks. Let's move on to the last use case and demonstration as part of this webinar. So there was a lot of things that we did on requirements. We started the presentation really with requirements when we were developing this electric vehicle, and we will also finish the webinar today on requirements. So there was a lot of things that we have done on requirements. We have been authoring requirements, we have been analyzing and decomposing these requirements, and we have been tracing these requirements. But there's one thing that we have not been doing. Envision there is a bug in your requirements, the functional definition of your requirements. So that means if you later on decompose that and implement it and so forth and trace that, is good. But if the problem was already, let's say, implemented in the beginning, you will not necessarily uncover it throughout the whole process. So meaning it will finally end up in your implementation. So much better way of working, and what is now coming on top to make the whole story complete, is our solution for requirements test and simulation. So meaning we have a product called Stimulus, which is our textual requirements simulation solution. The idea behind that is when you start to work on your requirements, create your requirements, you should already start in a very early phase to test these requirements and test in terms of figuring out, are these requirements correct? Are they consistent to each other, or is there something missing in your requirements? So that you continuously do this test and further refine these requirements. We are talking about functional requirements, and most of them will usually end up in a piece of embedded software. And once you will be coming to a point where you have created then also an implementation for your software, and you want to test this piece of software against the previously tested and validated requirements. So you can do on the one hand side test and validation on the left side of the V, but when it comes then later on to test the implementation, you can use the previously qualified requirements as a reference. So what we are wanting to do now in this next demonstration is we want to look at the left side of the V and see how we can simulate, debug, and introspect more deeply our requirements. So for that, I've set up a little example for today. It's a little headlight example, which from an architectural standpoint of view consists primarily of 4 different things. One is the headlight that is supposed to illuminate our surrounding we have on the other side a little controller that finally controls the operation of the headlight depending on the input. So meaning we have a switch that can turn on and can turn off the light manually, or when you put the switch into auto mode, we have a light intensity sensor, and depending on how much light intensity is being detected from the environment outside, the headlight is being turned on and off. So meaning from a functional standpoint of view, what we want to implement in our requirements is primarily this functional description here. So you see when the headlight goes below 60%, after a certain while with a little delay, we want to turn on the headlight. And then when the light intensity goes beyond 70% with a certain delay, we are going to turn off the headlight again. And we have a little hysteresis that we want to implement, because otherwise it could be that we have permanently this headlight flashing on and off. So this would be here a set of functional requirements that are supposed to describe that behavior. So we have, for instance, the two requirements that say what happens when the switch mode is in on and off mode, then the headlight shall be off and on. These are, I would say, the quite boring ones. They're pretty simple and easy. The more challenging one is this one, when the switch mode is in auto and everything is controlled by the light intensity, where we say, okay, if it's beyond 70%, then the headlight shall be off. Is below 60% after a certain while, headlight shall be on. If it's somewhere in between in hysteresis, it should be stable. This looks like a very simple system, but I can tell you, when we do this with our students, this exercise here, I've never experienced that somebody did it right at the first time. So my question is, when you look into this, is this specification of requirements really correct? Is it consistent? And is it really complete, or are there requirements missing? It looks pretty trivial, but I can tell, as always, the devil is in the details. So let's use our powerful solution, Stimulus, to put these requirements into Stimulus and to simulate and figure out if we have done a good job on the definition of the requirements. So you see here the requirements, and they are written really like in a natural language. You don't need to have a complicated modeling language. They are written like in a natural language. So I've created a test bench to test these requirements. The switch, I have a sensor for the light intensity that produce input signals, stimuli, and behind this one here are finally the requirements that model the functional behavior of the controller. I've defined different levels for the requirements. When I double click on this box here, I see again the requirements that we have sketched out previously. All right, so this system already allows us to do a simulation of the requirements. Let's simulate a couple of steps here in Stimulus. So the green curve is actually the light intensity. You see this changing over time. And we have two horizontal bars, the 60 and 70%, and the blue curve is the headlight. We see already there is some areas where we have these dashed lines. The dashed line is always a bad sign, because it means that the behavior of the system is not defined at these point in times. Let's go a bit more into the details to see what is happening here. So when we select this headlight signal, we see at this point here, it's a solid line, so meaning it's clearly defined. And we see, for instance, here, when we click on that, one requirement is active. So the gray ones, these requirements are not active. So we can easily debug which requirements are active. And this is a powerful thing in Stimulus. If you go one step further, we see this, all requirements in gray, none is active. It's quite simple, because we are beyond 70%, but the 3 seconds have not elapsed. And we have not stated here what happens in between. Now we just said after 3 seconds, we want to switch the light off, but we haven't said what happens in between when the 70% are crossed, but the 3 seconds have not elapsed. And this is also the reason why you have this dashed line here. The behavior of the signal for the headlight is not defined. So we have a hole in our requirements. Once the 3 seconds have elapsed, we see the requirement here is becoming active. We have one requirement active. So let's do something stupid now. We have now looked at the first example where we figured out a missing set of requirements. Our requirements are not complete. Let's look at a set of requirements that are now conflicting. We add another requirement here and say when the switch is in auto, headlight shall be on. We know that this one is wrong, because when the switch is in auto mode, we want to have the headlight controlled by the light intensity. So there should be a conflict coming up. Okay, let's simulate that system too. We see right away there's an error message coming up, and Stimulus has detected there's a conflict. So there is actually a condition requested that we should have 2 assignments to that headlight signal that are not defining exactly the same. So let's look into the details. What is happening here? So when we go to the area where the problem has been detected by Stimulus, we can see that there is actually 2 requirements active at the same time, this one, and both are stating something differently. We say, okay, headlight shall be off and headlight shall be on. How can this be? Well, when we go back a little bit in time, we are here above 70%, but the 3 seconds have not elapsed. Previously, we had a missing requirement. Now we have this additional that covers this one. But this is becoming a problem when the 3 seconds have elapsed, because this one is now also becoming active. So it means we have now 2 conflicting requirements. Yeah? So this is the power of Stimulus, all these debugging capabilities. And of course, Stimulus is also connected with the 3D experience platform, because aside from simulating requirements, we also want to manage the requirements data. And it's again a task that is being directly in the 3D experience platform. So I've created a requirement specification here, which is empty in 3D experience. You see there's no objects in it. And what we are wanting to do now is that we are wanting to push these requirements directly from Stimulus into the 3D experience platform to manage the data in the platform. So I connect to the platform and say into which requirement specification I want to move these requirements objects. So now I export in the next step the requirements. I select the ones that I want to move over. And now I can actually move them over into the specification in 3D experience. And once we have defined that step, we can push the OK button, and then the data is going to be exported to the 3D experience platform. And we can also do it the other way around, that we pull data from 3D experience. So it's a bidirectional process. Stimulus simulates the stuff and 3D experience manages the stuff. So we now see that the requirements have been exported into 3D experience. See, all of them have also a revision. And this is the detailed set of requirements that we have pushed into the platform. All right, I think this is also a nice example to also close this webinar. I hope you have enjoyed the different use cases and also enjoyed the demonstrations that we have shown. There's many, many more things that we can do with our model-based systems engineering solution, but of course we have just a limited set of time available. But nevertheless, so I'm still here. If you have any questions, I'm very happy to answer your questions now after the presentation. Thank you for listening and attending.